Swayam Prabha. Digital India. Educated India.
Welcome to the first lesson of the 8th module, which is on combined stresses part 1, or more precisely let us call it as the stresses which are developed due to the combined actions of loading in the members. In fact, so long we have discussed the action of different kinds of forces in the member which are acting in an individual form. Say for example, when we have discussed about the axial force in a bar, the force was acting normal to the section and we have computed the corresponding stresses which we have called as normal stress. Subsequently, we have looked into that if a pressure vessel is subjected to pressure, we have computed the stresses on the outer shell which is in the circumferential and the longitudinal direction. Subsequently, we have computed the stresses in a bar which is subjected to another kind of forces which we have called twisting moment. And then lastly, we have evaluated the stresses in the bar corresponding to another kind of force which we have called as the bending and the shear force. We have seen how to compute the bending moment and shear force in a beam which is subjected to transverse loading, and consequently we have computed the values of stresses which we have termed as bending stress and shear stresses. Now, in all these cases you have noticed that we have computed these stresses for the individual loading, and thereby the stresses were for those individual loading actions. Now, we are going to consider the case where if these loads act simultaneously in a particular member. So, what will be the consequence of the simultaneous actions of these loads, and what will be the thereby the combined stresses in the member. Hence, once this particular lesson is completed, one should be in a position to understand the concept of combined loadings and thereby the combined stresses in members. Also, one should be in a position to evaluate the stresses in structural members that develop due to such combined loadings. The scope of this particular lesson includes therefore, well, as we do the recapitulation of previous lesson, we will be looking into the answers of the questions which I had posed last time, and in the process we will recapitulate some of the aspects of the previous lesson. In this particular lesson, we will make use of the developed formulae for evaluation of stresses for the combined actions of loadings. Now, as we have noticed that in earlier cases for individual loading situations, we have arrived at different stress formulae. Say for example, when a member is subjected to a twisting moment, we have seen that what is the relationship between the shearing stress and the torsional moment. Consequently, we have looked into that if a member is subjected to bending, then what is the relationship between the bending stress and the bending moment, and also the relationship between the shearing stress with the shear force. Now, all these aspects we have looked into, as I said, in an individual form. Now, in this particular lesson we will look into if there are actions of these loadings which are acting simultaneously or which are getting developed simultaneously because of some practical situations. Now, how do we compute the values of those stresses because of such combined loading forms? Also, once we will look into the examples for evaluation of stresses in structural members due to such combined loadings. Well, let us then look into the answers to the questions which were posed last time. The first question was, what will be the value of deflection in a simply supported beam which is which is a simply supported beam, if the moment of inertia is double. Now, you must have noticed that while computing the value of the deflection, we make use of the moment of inertia of the cross section, and these are the expressions for the deflection values which we had evaluated in the previous lesson. Now, if we have a simply supported beam which is hinged at end A and is supported on a roller, thereby it is a simply supported beam which is subjected to uniformly distributed load, and let us say the intensity is Q per unit length. Now, for this kind of loading on a simply supported beam, the value of the maximum deflection delta is 5 QL4 by 384 EI, and this we have seen we can evaluate this either using the differential equation for the beam deflection, or we can make use of moment area theorem and we can compute the value of this deflection, which we have seen in the previous module. Also, if the same simply supported beam but is subjected to a concentrated load at the center, then the value of the maximum deflection is PL cube by 48 EI. This also we have seen in the previous module. Now, if you look into these two expressions, here the moment of inertia value, which is I, comes at the denominator of this expression, and the delta value is inversely proportional to the moment of inertia I. Now, therefore, irrespective of the loading what you have on the beam, if this moment of inertia is double, instead of I it is twice the I, then the value of the delta will become half than what it was earlier, and so is the case in this particular situation. So, this particular question which was posed, which is quite general in nature, wherein we have not talked about the loading on the beam, we have not talked about the span as such or the length of the beam, but what we said is that if the moment of inertia is double, then what is the impact of that on the deflection. Now, as we can see from this expression of the deflection, whether it is uniformly distributed load or a concentrated load, if the moment of inertia is double, the deflection is going to be half of the previous value, and this is what is the relationship between the deflection and the moment of inertia. Now, consequently, the second question was what will be the value of end slopes in a simply supported beam if the span is doubled. Now, this particular question also is quite general, because we are talking about that if the length of the beam or the span, if it is double, then what is the consequence on the end slopes that will be generated in the beam. Now, here if you look into, you see the values of the end slopes as we have computed for these two different cases, when the beam is subjected to uniformly distributed load of magnitude Q per unit length. We have computed the value of theta b and theta a, and we have seen the magnitude is QL cube by 24 EI. Now, if the same simply supported beam, if subjected to a concentrated load at the center, the value of the end slope comes as PL square by 16 EI. Now, if you look into the expressions carefully, you will find that here the span is having a power of 3, and here the span has a power of 2. So, it is very difficult that way to say that in a general form, that if the span is double, then what will be the consequence of the slope. Now, we can say that if the beam is subjected to a uniformly distributed load, then the end slope will be, since L becomes twice L, so it will be 8 times of the previous value, whereas for a concentrated load, if L becomes twice L, it will be 4 times of the previous load. So, what we can say is that if the span is double, then the value of the end slopes are going to be increased, or it is going to be more than the previous value, but it depends on that what kind of loading you have on the beam. If you have uniformly distributed load, as we can see over here, it gets 8 times of the previous value, whereas when you have a concentrated load at the center, it becomes 4 times of the previous values. Now, depending on the type of loading you will have, the values of the slopes will change, and accordingly if span is double, it will be multiplied by a factor, but it is quite obvious that the slopes are going to be larger if the span is double. The last question we had was what is the value of slope at the tip of a cantilever beam subjected to concentrated load P at the tip of the beam. Now, the cantilever beam, as you know, is fixed at one end and is free at the other, and is subjected to a tip load P at the end of this beam, and we had computed that the value of theta b, the slope at end B, is equals to PL square by 2 EI, and as you can compute it very quickly using moment area theorem. Now, as you know, the bending moment diagram, if you draw it, it is a triangular one having the value of this particular ordinate as PL by EI, that is the M by EI diagram, and as you know that the slope of this particular end with reference to the tangent drawn at this particular point is nothing but area of the M by EI curve between A and B, and which is equals to half times PL by EI multiplied by the length, and that gives you PL square by twice EI. So, that is the slope, and the negative sign indicates that it is moving in a clockwise form. According to our sign convention, this clockwise rotation is negative, and this is the magnitude of the end rotation when a cantilever beam is subjected to concentrated load at the tip of the beam. Well, these were the answers of the questions which were posed last time. Now let us look into that if the members are subjected to, or on what situations a member is subjected to the combined actions of loading. Say this is an example where this helicopter blades, they are connected to this rotor. At this particular point there is a shaft which is like this, and this particular shaft is, when this fan rotates, gives a twisting moment to this shaft, and also in the process that when the fan moves and gradually it gets lifted up, the shaft experiences a pull in the vertical direction. So, this particular member, if we look into the shaft part of it, it is subjected to a load P, which is an axial pull. At the same time, it is subjected to a twisting moment. So, at a particular point of time, the shaft may be subjected to the combined actions of this axial pull and the twisting moment T. Now, as you have seen from the previous cases, when we have discussed individually these loading actions, when a member is subjected to axial pull, it is subjected to a normal stress, which is P divided by the cross sectional area. Also, if a member is subjected to a twisting moment, then there will be shearing stresses generated, as we have already observed. Now, when you have the combinations of these two, that means the member is subjected to axial pull, at the same time it is subjected to a twisting moment, that means there will be both normal stress as well as the shearing stresses. So, we will have to compute these individual stresses and then combine them together suitably, so that we can arrive at what could be the maximum possible stress that can generate in the member at any point. And as designer, we are concerned with that, what is the maximum possible value of this particular, of any stress that can generate in that particular member, and we must safeguard the member against that maximum value of the stress. Now, let us look into another example where we come across the combined action of the loading. Here you see this beam member is hinged at this particular end, is pinned, and at this particular end it is connected with a cable. Now, the member is loaded in the transverse direction, let us call by load P1, P2 and so on. Now, if we take the free body of this particular member, if we take a cut in this cable, and if we take the free body of this particular part, now the end reactions will be represented by the horizontal, vertical and the horizontal reactive forces. Then we will have this force which will be acting in the cable member, and if we take the component of this cable, one will be in the vertical direction, let us call this as F1, another will be in the horizontal direction, let us call that as F2. Now, this horizontal force, the vertical force, now when we take the summation of horizontal forces equals to 0, we get the value of the horizontal reaction, which is equivalent to F2, H is equals to F2, and this force is acting along the central line of this member, or the centroid of this member, and thereby this is going to cause, if I take any cross section, then the stress at that particular section because of this load will be the axial load, if we call that as H, divided by the cross sectional area, and that is the normal stress that we will have. Now, apart from that, since this particular beam is acting with these supports, the vertical reaction here, and the vertical component of this particular force also is going to hold this particular point. So, the whole member will undergo a deflection because of this load, and there will be bending moment and shear force developed in this particular beam, and because of the bending and the shear there will be bending stresses, and bending stress, as you know, again is a normal stress which will be acting in the section in terms of the compression and tension. So, there will be compressive forces generated because of this axial force, there will be compressive and tensile stresses generated because of bending, and there will be stresses generated because of the shear. So, at any section if we look into, there will be normal stress, there will be the normal stress because of axial force, there will be normal stress because of the bending, there will be shearing stress, and finally we will have to combine this normal stress and the shearing stress to find out that what is the value of the maximum stress, which we call as the principal stresses. As we have seen in module 1, that if you have the normal stress and the shear stress, how do you compute the values of the principal stresses or the maximum normal stresses. So, as you can see here, now it is not only the axial force or the bending stresses alone, we have the actions of the axial force as well as we have the actions of the lateral force which is causing bending in the member, and thereby such members are subjected to the combined actions of loading and thereby the combined stresses. Now, let us look into another example wherein we come across the combined loading actions. Now, we have already seen earlier that if a pressure vessel is subjected to internal pressure P, then how do we compute the longitudinal stress and the circumferential stress, which is sigma, which we have called as a hoop stress, circumferential stress sigma as PR by T, and the longitudinal stress which is equals to PR by twice T. Now, these stresses we have computed individually for the pressure which is acting inside. Now, if you look into that, this particular pressure vessel is supported at this particular point and at this particular point. Now, naturally because of its own weight along with the liquid, it will undergo bending over this particular part, and because of this bending there will be stresses generated in this pressure vessel. So, apart from the stresses which we get from the internal pressure, we will have the stresses generated because of this supporting point. As a beam, it is getting supported at these 2 points, and thereby there will be deflection of the member and there will be stresses generated. So, we will have to account for both the stresses, so that finally the resultant stress which we get, which we call as a sigma, they are the combinations of the internal pressure stress and the stresses which are getting generated because of the bending. So, again this is an example for the combined loading situation. Now, this is another case where we get the values or the loading in combined form. Let us say this is a shaft, and this particular shaft is subjected to or is attached with a gear where we have a couple which is giving a twisting moment in the shaft. Also, if you look into this particular shaft, is having a member which is eccentric with respect to the shaft center line, and there is a concentrated load acting at the end of this particular member. Now, this particular load, if we transfer to the shaft center line, this will be along with a couple which is going to be a twisting moment in the shaft. So, if we take the idealized form of this particular shaft, this is supported at this particular end, this is supported at this point through this particular support, and at this particular point where this overhang is there, the force is transferred to the shaft center line, and thereby there is a concentrated load along with a twisting moment that is acting over here, and also at this particular end we have the twisting moment that is developed because of this gear, and if gear has some weight, then here also there will be a concentrated load acting at this particular point. So, if you look into this particular member over this particular length, now this is supported here, and on this part it is overhang. So, it is a kind of a overhang beam subjected to a concentrated load at this center, subjected to a concentrated load at this end, and subjected to a twisting moment at this particular point and at this particular point. So, this particular shaft is not only subjected to the transverse loading which will cause the bending in the member, thereby we will have the bending moment and the shear force, and consequently we will have the bending stresses and the shear stresses. Also, because of the twisting moment there will be shear stresses in the shaft. So, there will be combined stresses or combined shear stresses because of the shear force and the twisting moment, and there will be normal stress because of the bending. And now once we have this bending stress and shear stress, then we can compute the values of the resultant stress, as we have seen earlier in module 1, that using Mohr circle we can find out the value of the maximum normal stress, which we have called as principal stresses, using the normal stress and the shear stress values. So, you see in this example also this particular shaft is subjected to the combined actions of the loading. Let us look into another example which is quite common, that in cities you must have noticed that for giving directions for different places, a board is used, and this particular board is connected to a vertical shaft through this particular joint, and this board is projecting from this particular vertical shaft. The vertical shaft is connected at the base by some rigid support. Now, this particular board which is projecting from the shaft is exposed to the forces like wind. Now, when the wind load acts perpendicular to this particular plate, let us say the action of this resulting wind load which is acting at the center of this plate is P. Now, basically since this board is connected to the vertical shaft or the vertical rod, now this load will be transferred to this, because finally the load has to be transferred to the base below. So, this force if we transfer to the vertical member, then it will be associated with a moment, and this particular moment will be acting about the axis which is normal to the vertical shaft. Now, and this moment we call generally as the twisting moment. So, if we look into the idealized form of this particular configuration, if we look into the idealized form of this vertical shaft, this looks like this, that it is one end of this member is connected which is simulating this particular support, other end is free, and at this particular point the load, concentrated load is getting transferred to the shaft along with a twisting moment. The vectorial direction of this is this, and it is the twisting moment is acting in the member. Now, because of this transverse load, the beam will be subjected to a bending moment and there will be shear force as well. So, this beam will have the actions of bending moment M, will have the actions of shear force. Also, we have the twisting moment T, which will give rise to the shearing stress tau, bending will give rise to the normal stress sigma, V will give rise to the shearing stress tau. So, you see that this particular member is subjected to the action of bending moment, shear force and the twisting moment, and thereby we will have the resulting normal stress and the shearing stresses, and for each individual load we can compute the values of the normal stress and the shearing stresses, and once we know the values of the normal stress and the shearing stress, then we can compute the resultant stress in terms of the normal stress and the shearing stress. Well, let us look into this again. If we go back to the expressions which we have already derived. Now, for in the first module we had looked into that if you have a axial load in the member, then the stress, normal stress, we compute as sigma equals to P by A. Subsequently, we have seen that if a vessel, pressure vessel is subjected to internal pressure, then it will be subjected to stresses which we have called as hoop stress or the circumferential stress, which is equals to PR by T. Also, we have computed the longitudinal stress, which is PR by twice T. Then subsequently we have looked into that if a shaft is subjected to a twisting moment or a torsion, then the torsion formula is T by J is equals to tau by rho is equals to G theta by L, and this indicates that from these first two equality we can compute the value of the shearing stress tau, which is equals to T rho by J, and so if we know twisting moment we can compute the value of the shearing stress. And subsequently we had looked into the bending formula where the moment is related to the bending stress sigma, and we know that sigma is equals to minus my by I. So, sigma, the bending stress, is related to the bending moment m, and also we had looked into that if you have shear force V, then the shearing stress tau is equals to VQ by IB. Now, these are the individual cases as we have evaluated earlier. Now, we will make use of in this particular lesson as such, we are not going to derive any formulae, but we will make use of this formulae which we have derived earlier for individual load cases. Now, depending on the situations wherever we will have combinations of these stresses, we will make use of those individual formula and combine them suitably to arrive at the resultant stress in the member, because finally we are concerned with that what is the maximum possible stress that can be generated in a member because of such combined loading actions. Well, now let us look into a case where we get a combined loading form wherein we have a vertical member which is fixed at the base, and at the top we have a rigid bar on which a load P is acting, which is eccentric with respect to the center line of this member or the CG of this vertical member. Now, if we transfer this load which is eccentric with respect to the CG of the vertical member, if we try to transfer to the center of gravity of this vertical member, then what happens? This load we transfer over here, and since here we did not have any load, so we will have an opposite load, and this opposite load along with this will form a couple. So, the transfer of this force to the CG of this particular vertical member is a load and a moment, and this is what is shown over here. Now, if we remove this vertical bar, this horizontal member, then on the vertical bar we have the effect of this eccentric load as a load P, which is concentric now, which is acting through the CG of the member, and we have a moment which is equals to P time E, where E is the eccentricity or the distance of the CG from this loading point. Also, this particular member is subjected to a concentrated load P1, which is acting at a distance, let us say A from the support. Now, if we idealize this particular situation, then probably we can describe the same thing in this particular form, that we have a cantilever member which is fixed at one end and the free at the other, and at this end we have a concentrated load P which is acting through the center of this particular member along with a moment M, bending moment M, and we have a transverse load P which is acting at a distance of A from the support. Now, the actions of these loads will be that the concentrated load P which is acting through the center of gravity of the member will cause a normal stress. It is like a member is subjected to a compressive load. So, at any cross section if we compute, the stress will be P divided by the cross sectional area, which we have called as normal stress. So, this is what is indicated over here. The stress distribution is uniform, which is P by A. Now, since this is compressive, so we have called this as C, it means it is a compressive load. Now, because of this bending moment M, at any section if we compute, now on this side of the load it will be just the M, but if we take a section over here and draw the free body, then there will be moment due to this lateral load or the transverse load and the external moment M. So, at any section we can find out the bending moment because of this transverse load P and moment M, and if we call that moment as M, then the corresponding stress in this member will be My by I, as we have seen in case of, if we call this as M dash. M dash is the combination of M and P, effect of P, and finally we get the bending stress which is M dash Y by I. Now, this is going to cause the tensile and compressive stress. Now, physically if you look into this particular member, when it is subjected to the action of bending in this particular form which is in a clockwise direction, and this particular load is also going to cause a moment in a clockwise direction, on this phase, on the top phase we will get a tensile stress, and at the bottom phase we will get a compressive stress. Now, and this is what is indicated over here, that we have a stress distribution which is tensile at the top and compressive at the bottom, and which is varying linearly across the depth. Now, if we combine these two stresses, since we are writing in general terms P and M, now there could be three situations. Now if I draw a section through the, or if I draw a line through the neutral axis, below neutral axis the member is always under compression, under the action of axial load and under the action of the bending, both are subjected to compressive stresses, and thereby below neutral axis you will find that you have always the stresses as compressive stresses. But at the top there could be different situations like if P by A, the direct normal stress which we get, which is a compressive in nature, and bending stress is causing a tensile stress at the nature. If tensile stress is larger than this compressive stress, that means if M dash y by I, if it is greater than P by A, then we will get a tensile stress at the top. If this My by I is equals to P by A, then at the top we will get a stress which is equals to 0, and if M dash y by I is less than P by A, then we will get that a stress which is compressive at the top. So you can get either this configuration or this configuration or this configuration, depending on the magnitude of the axial load P and the bending moment M. So at the bottom, because since the axial compressive force is giving a compressive stress everywhere, and the bending is giving the compressive stress at the lower part of the below the neutral axis, the bottom zone always you have the compressive stress, whereas in the upper zone you can have either tensile stress or compressive stress or zero stress, depending on the magnitude of the bending and the axial force you have, and this is what is represented over here. Now we can take another example of this kind of combined stress situation, where the beam is a simply supported one, having a support, a hinge support on one end and a roller support at the other, and is subjected to a compressive force P, and you have transverse load, let us say P1, P2, P3. Now this compressive force, which is acting through the center of gravity of the member, at any cross section if we take, the stress will be P divided by A, which is compressive in nature, which is indicated over here. But this transverse loading which is acting in this beam is going to cause the bending of the beam. This is going to deflect, and thereby there will be bending of the beam, and physically if you look into, the lower part will be under tension because of this loading, and the top part above neutral axis will be under compression. So this is what is indicated over here, that if we compute the bending stress, which is My by I, will generate the compressive stress above the neutral axis, and we will have tensile stress at the below the zone below neutral axis. Now if we combine these two together, then we will have the compressive stress, then the neutral axis position of course will shift, and you will have the compressive stress above the neutral axis and the tensile stress at the bottom if My by I is greater than P by A, or this part will be 0 if My by I is equals to P by A, and this will be positive stress or the compressive stress if My by I is less than P by A. Now again we get the similar situation at the top, only thing the position changes over here. We get compressive stress always at the top, but the bottom part of it, either it could be tensile or could be 0 or could be compressive, depending on the magnitude of the axial load you have, depending on the magnitude of the transverse load you have, and consequently how much bending moment it is generating and how much is the bending stress it is generated because of this bending. Now once we combine these two loading conditions together, then we can get the effect of the combined stresses in the member, and we can see that whether the material can withstand the maximum value of the stress that is getting generated because such combined actions in the member, and that is what is our objective in these particular situations. Now if we look into the effect of such combined loading in the member or at different points about the stresses, as you know that it is going to produce the normal stress sigma, the axial force, the lateral force is going to cause the normal stress sigma and the shearing stress tau. So we are going to have total normal stress sigma and we are going to have the shearing stress tau, and finally we need to compute the value of the resultant the stress because of this normal stress and the shearing stress. Now if we consider a small element in this particular zone which is above the neutral axis, but below the top surface of the beam, then the stress we can represent in this form. If we enlarge that particular part, we will have a compressive stress which is the normal stress, and this normal stress is because of two actions. One is P by A, which is because of the axial force acting in the member, and another one is because of the bending, which is equals to My by I, and this is going to give us the compressive stress again at the top of the beam or above the neutral axis. So that is why it is summed up together, but basically this is negative stress because it is acting in the opposite direction of positive x, and these of course if we take the sign conventions properly, or if we take say axial pull is compressive force is negative, the bending also is causing compression at the top, so that is negative. So if I sum them up, it is going to give me the negative stress, and which is acting in the opposite to the positive x direction, and that is what is indicated over here. And we have the value of the shearing stress tau, which we have seen is computed as VQ by IB. So this is the shearing stress tau, and this is the normal stress sigma, and once we have the sigma and tau, as you know that we can plot them in the Mohr circle, and we can get the value of the maximum value of the normal stress. So you have sigma and tau, and here the sigma is 0 and then the tau, and if we join them together, this is the center. If we draw the circle, then this is going to give us the maximum value of the normal stress, which is sigma 1. So at that particular point, we can compute this value of maximum normal stress and the minimum normal stress, and also what is the value of the maximum shearing stress. Now if we consider a point which is on the neutral axis, then the stress distribution can be indicated by this. Now as you know that because of the bending stress, which is My by I, at the neutral axis level, the value of the bending stress is 0. You have the compression and the tension depending on the nature of the moment, but along the neutral axis the stress is 0. So when we are considering a point on the neutral axis, there we will have the normal stress because of the axial compressive force only. There won't be any normal stress because of the bending, and that is what is indicated over here. As you can see that the sigma is equals to P by A on this particular element, and consequently we have tau equals to VQ by IB, and incidentally the shearing stress at this particular location will be maximum, as we have seen. So again we will have the normal stress sigma and the shearing stress tau, and based on these values we can compute the value of maximum principal stresses. And in the third point, which is below neutral axis, if we plot the stresses, now here assuming that the compressive stress or the stresses, tensile stress which is getting generated because of the bending, which we are computing from My by I, is larger than P by A, and thereby there is resulting tensile stress below neutral axis. And if that happens, then the normal stress which we have over here is shown as a tensile pull, and along with that we have the shearing stress tau. So again based on this sigma and tau, we can plot in the Mohr circle that what will be the value of the normal principal stress sigma 1 and sigma 2. But only aspect you should keep in mind now that here sigma is in positive, in earlier case sigma was negative. In fact earlier we had to draw sigma in the opposite direction, which is in the negative direction, and tau in the positive direction. So this is what we get, and consequently the values of the normal stress and the shear stresses will be like this. In this particular zone, sigma x is equals to P by A minus My by I, and we presume that My by I is higher than P by A, and thereby we get a tensile pull, and the shearing stress is equals to VQ by IB. Well, now so long whatever we have considered, that basically we are combining the individual actions of the load. That means whether you have the axial load or the transverse load or a twisting moment, what we are trying to do is we are trying to compute the stresses for the individual actions and combining them suitably, either when you have total normal stress or the shearing stress, and then we are combining them through Mohr circle. Now the question is that these are basically are nothing but the superposition of the stresses of the individual actions. Now this is possible if when we are talking about this axial load and the lateral load or the transverse load which is causing bending. Now this is possible if the slope of the deformation is small. Now, if we get a very large deformation of the member, then this kind of superposition is not allowed, and you cannot calculate the combined stresses in this form the way we are calculating at the moment. Means that if you have the axial pull and if your deformation is large, now at any point where the deformation is delta, then you will have the value of m because of this p is equals to p times delta. Now, this moment if we add to the bending moment, let us say m dash, then if this m, I mean with suitable sign plus or minus, now with m dash and m, if they are comparable because of this large deformation, then this superposition of stresses will not be allowed. But if the value of m is insignificant in comparison to m dash, where delta is small, then we can ignore this and we can use the superposition, and we can compute the values of the stresses at different point because of these combined actions. And this is one of the important aspects should be kept in mind. Well, then having discussed these actions of different loads or the different load combinations, let us look into some example where a member, a beam member which is fixed at one end and free at the other, which we call as a cantilever, is having a bracket at this particular end and is subjected to a pull of 100 kilonewton at this bracket. So, a 100 kilonewton force is applied to the bracket as shown in the figure. Now, what you need to do is that compute the normal stresses developed at points A. Now, this point A and point B is on the outer surface of the beam at the top and the bottom surface. So, you got to compute the normal stresses developed at points A and B. Now, given that the cross section of the member is a T and the cross sectional area is 8000 millimeter square, and the value of the moment of inertia is equals to 50 into 10 to the power 6 millimeter to the power 4. Now, here the position of the neutral axis for the section is given, and the neutral axis is at a distance of 100 millimeter from the top surface, and from the bottom surface it is 200 millimeter. Now, this particular member, which is the force which is inclined, this is inclined at an angle of 17.5 degree with respect to the horizontal, and the position of the load which is acting in the bracket is at a distance of 100 millimeter from the top surface of the beam, and the position of this bracket from this end is 1 meter. Now, what is the action of this particular load? This particular load which is acting at this bracket point, we can decompose in two parts. We can decompose in the horizontal direction, we can decompose this in the vertical direction, since we know this angle theta. Now, this particular horizontal load which is acting at the away from the top of the beam, if we transfer that beam to the load to the CG of the member, and then thereby it will be an axial pull to the member, but if we do that, it will be associated with a moment. So, this load can be transferred to the CG of the member with a load and a moment, and the vertical component of the load is going to cause a bending in the member. So, let us analyze that first, that how do we do that. Now, here this 100 kilonewton load is acting at an angle of, let us say, theta, which is equals to 17.5 degree here. Now, the first step is we decompose this load into two directions. One is P1, another one is P2, and P is 100 kilonewton. So, P1 is 100 cos 17.5 degree. So, this is equals to 95.4 kilonewton, and the vertical component of this P2 is equals to 100 sin 17.5 degree, which is equals to 30 kilonewton. So, we have two force components of this 100 kilonewton axial pull, which is P1 and P2. Now, this P1 is acting away from the CG of the cross section of this member. Now, if I transfer this horizontal load at the CG of the member, then it will be associated with a moment as it is indicated over here. Now this load P1 is transferred to the CG of the member and it is associated with moment M, which is equals to load P1 times this eccentricity E. So the value of the moment M is equals to P1 into E, which is 95.4 is the axial pull and 0.2 is the distance E, and that gives you 19.08 kilonewton meter is the moment. So we have the value of the moment and the axial pull. Now this axial pull is through the center of gravity of the member, and thereby it gives a normal stress at any cross section. Now we have the bending moment M1 acting at the end, and we have the transverse load P2 which is acting at a distance of 1 meter from the support, which is acting 1 meter distance from the support. Now let us look into the what is the actions of this load individually. Now if we have this, that axial load P1 which is acting at the CG of the member, now this is going to give us a normal stress. Now at any cross section, if we compute the value of the stress sigma, which is equals to P1 by the cross sectional area A, and we have called that as say positive stress because it is tensile, and according to the sign convention our tensile is positive. So tensile stress, axial tensile stress, we have called that as a positive. So sigma is equals to P by A, which is 95.4 into 10 to the power 3 so much of Newton divided by 8000 millimeter square. So this gives us 11.925 megapascal. Now let us look into the action of this bending moment M1. Now this moment M1 which is acting at this end, for this at any cross section if we take a free body, we will get that M as negative of M1, and therefore this is the bending moment diagram where the bending moment is negative everywhere. Now because of this, as you can see even physically, that at the top we get a tensile stress, at the bottom we get a compressive stress, and as we know the tensile we designate our sign convention is positive and compression is negative. Now if we compute the value of sigma, which is my by I, sigma equals to minus my by I, and m is negative, y at the top is positive which is 100, and I for this member is 50 into 10 to the power 6. So we get a value of plus 38.16 MPa. So this is the value of the stress which is acting at the top of the beam. Now consequently if we compute the stress sigma b at the bottom of the beam, this is equals to again minus of m. Now y, since it is downwards, so it is minus, so thereby we get a minus sign, minus 76.32 MPa, which is compressive at the bottom. Now let us look into the action of this particular load, which is a vertical load at a distance of 1 meter from the support. For that if we draw the bending moment diagram, the bending moment diagram is a triangle, and the value of this is equals to P2 into 1 meter is equals to P2 kilonewton meter, and P2 is 30, so its one is 30 kilonewton meter is the moment over here. Now this is a positive moment. Now if we compute the stress at the top, now because of this the bending which is going to happen physically, this member is going to be lifted up in this form. So we will have tensile stress at the bottom and compressive stress at the top. So as per our sign convention, this is negative at the top and positive at the bottom, and that is what is represented here. Now stress sigma is equals to minus my by I, m is positive, so this is minus 60 MPa, so giving the negative or the compressive stress at the top. Sigma b, the stress at the bottom, is equals to my, y is minus 200, so this is plus 120 MPa. So these are the values of the stresses that we get at point A and B because of three individual loading actions. One is the axial pull, another one is the moment, and another one is for the vertical load. Now you see that the inclined load which we had, that we have first we have decomposed in horizontal and vertical direction, and the horizontal load which was away from the center of gravity of the beam, we have first pulled that load into the CG line, and when we do so, since it is eccentric loading, it gets associated with a couple. So the cantilever beam now is subjected to this axial pull which is concentric, then we have a moment, a couple acting at the tip of the beam, and we have a vertical load which is acting at a distance of 1 meter from the support, which is causing a bending in the beam. So, we have seen the 3 individual actions. Now this is a case of a combined stresses. So, we combine them together, we individual stresses we join them together to get the final effect at point A and B. Now, if we do that, so at A we will have plus of this and minus of this, and at B we will have plus of this, minus of this and plus of this. So, let us look into then finally what we get of the stresses. So, these are the values of the stresses that we get, that at A we have plus P by A, this is plus because of the tip moment M1, and this is because of the vertical load which is acting in the beam. So, resulting of this gives us minus 9.915, that means this is a compressive stress that is acting at the top of the beam, and at the bottom we get sigma B, which is equals to 11.925, which is P by A, minus 76.32, this is because of the couple, and this is because of the vertical load which is causing 120 MPa. So, finally, if I join these 3 together, we get a stress of 55.605 MPa, which is again tensile in nature. So, we have stress at A which is 9.915 compressive, and we have stress at B 55.605 MPa, which is tensile. Now, let us look into another example, which is we have a beam which is simply supported. The beam ABC is supported by a pin at A and by a cable at C at this point. Now, what you will need to do is you will have to determine the largest value of P, so that the normal stress in the beam is limited to 120 MPa. If the normal stress value is 120 MPa, then what will be the value of P? The cross section of the beam is 100 by 400. Now, if we look into the free body of this particular beam, it will be like this, that if we take the cut in the cable, there will be a cable force, let us call that as F, and again as we have done in the previous example, we take the components of this force in the horizontal and the vertical and the horizontal direction, and thereby if this is theta, now you see that these distances are, this is 4, this is 3, so this is 5 and this is theta. So, cos theta is equals to 3 by 5, which is equals to 0.6, and sin theta is equals to 4 by 5, which is equals to 0.8. So, f cos theta will give you the horizontal one. If we call this as say f1 and if we call this as f2, so f1 is equals to f cos theta, which is 0.6, f2 is equals to f sin theta, which is 0.8. Now, if we take the summation of horizontal force as 0, if we call this as h and this as v, h is equals to f1, which is equals to f into 0.6. Now, if we take the moment of the forces with respect to A, we have f2 into 3 is equals to p into 2, and thereby f2 is equals to 2p by 3. Now, f2 we have seen is equals to f into 0.8. So, f into 0.8 is equals to 2p by 3, or f is equals to 2p by 2.4. So, if this is f, then the vertical force f2 we have got as 2p by 3, and f2 plus v will give you p. So, v is equals to p by 3. Now, if we compute the bending moment because of this, now you can consider this as a simply supported beam subjected to load P over here, and thereby you will get a bending moment of this form, where the value of this is equals to 2p by 3 kilonewton meter if P is in kilonewton. So, this particular member will be subjected to the action of this axial force, which is F1, which is equals to F times 0.6, and F being 2p by 2.4, this is equals to P by 2. So, you have the axial compressive force of P by 2, and you have a bending because of the lateral load P, which is of magnitude 2p by 3. So, you have the action of axial stress, which is normal stress, and because of bending you are going to get the normal stress. Now, physically if you look into, because of this load P, at the top you will get compressive stress and at the bottom you will get tensile stress. Now, if we combine the compressive stresses because of the axial compression and the bending, we will get the maximum compressive stress, and if that we limit to 120, then we will get the value of the maximum stress. Now, if we compute the value of the maximum normal stress, this is equals to that P by A. Now, axial force is P by 2, that divided by A, plus my by I, which is m is 2 P by 3 into y is 200 and I is the moment of inertia, which is equals to 100 into 400 cube by 12. So, if we compute this, you will get the values as, and this is equals to the stress sigma, and sigma is equals to 120. So, this is equals to, if you compute, if you substitute the value of A as 8000, you will get this as 0.0125 P plus you have 0.25 P because of this. Now, if you combine these two, you get 0.2625 P, and this is equals to 120, and thereby you have the value of P as equals to 457 kilonewton. So, you see that we can compute the maximum value of the load P, which can be applied here, so that the stress does not go beyond 120, and here we get the combined actions of this axial stress as well as the bending stress. Well, we have another example problem that you need to determine the principal stresses and the maximum in plane shear stress at point A, which is at a distance of 20 millimeter from the centroidal axis, and it is subjected to a load of 50 kilonewton acting at the center of the beam in an inclined form, and you look into this problem. We will discuss about this in the next lesson. Well, then, to summarize, here in this particular lesson we have looked into the aspects of the previous lesson. We have recapitulated some aspects of the lesson we have already done in the last lesson. Then we have looked into the concept of different types of combined loading and thereby the combined stresses that is generating, and we have looked into some examples to evaluate the combined stresses in members, and after analyzing them properly for the individual loading cases, and what are the actions of finally the combined loading situation. And these are the questions given for you. How will you evaluate the combined stresses if the member is subjected to axial load and bending moment? How will you evaluate the principal stresses if the member is subjected to axial load and bending moment? And what is the value of normal stress on the neutral axis when the member is subjected to axial load and bending? Well, look into these questions, try to go through the lesson. We will give you the answers of the questions in the next lesson. Thank you very much. To the second lesson of the 8th module, which is on combined stresses part 2. In fact, in the last lesson we have discussed about, or we have introduced the concept of the combined stresses in a member, wherein a particular member is subjected to a combination of loads, say for example axial load and the torsion, or the torsion and the bending, or could be axial load and bending, and various combinations of these individual loads. Now, we have also looked into that how do you compute the stresses when a particular member is subjected to the combinations of these different loads. Now, in this particular lesson we are going to look into some more aspects of such combined loads and how do we analyze them, and thereby we compute the values of the stresses. Hence, it is expected that once this particular lesson is completed, one should be able to be acquainted with some more aspects of combined loadings in a particular member, and thereby the evaluation of the combined stresses in members.